Welcome to the debate. We are diving straight into one of the most persistent and, frankly, deeply technical arguments in C++ and systems programming, what I call the integer fault line.
Hmm.
This is the battle between signed and unsigned types. Do you use int or do you use size t or UN32T for things like indexing, sizing, and loop counting?
It might sound like a minor style choice, but it's really not. It's fundamental.
Oh, absolutely. It fundamentally impacts security, optimization strategies, and code correctness. It's an architectural decision. We are way past debating tabs versus spaces here. We're discussing which arithmetic model is fundamentally safer and more robust for modern systems.
Right.
Now, before we really plunge into this, and this is a very specific technical analysis informed by, years of experience, a quick word of transparency. This script was generated by an AI assistant, mainly to ensure total accuracy against the technical source material, but we guarantee the rigor and depth of the argument are far from typical AI slop.
Hey, good to clarify.
So the central question today is whether modern systems engineers should finally abandon the C legacy, the one embodied by SignedIt, and just fully embrace signed arithmetic for general logic. This follows strong advocacy from groups like Google and the C++ core guidelines. I'll be arguing that, well, signed integers are just unequivocally superior for most general-purpose arithmetic. They reduce exploitable security risks and enable much more aggressive compiler optimization.
And I'll be coming at it from a different angle. I agree, we have to manage the risk, but the idea of just abandoning unsigned types is, frankly, untenable. They aren't merely legacy. Unsigned types are absolutely necessary for semantic correctness. They're the only logical choice for modeling physical constraints like memory, for low-level bit patterns, and of course for consistency with the C++ standard library, which, defines the whole ecosystem.
My position is really rooted in practical safety and mathematical logic. Signed types align directly with how we think about math, and crucially, they prevent these catastrophic logic errors. The standard library's reliance on size t for container size, an unsigned type, is a vestige of a time when every bit mattered. We're talking about 16-bit architecture where memory was extremely constrained. That constraint is just obsolete, and the type choice that came from it is now an active liability.
Okay, but let me explain. The functional core of the problem is what we can call the subtraction trap. If you're using a signed type for, say, a counter, and you subtract 1 from 0, you get -1. Simple, predictable. But if you're using an unsigned type, that same operation, 0 minus 1, causes an underflow. It results in the maximum possible value, a number close to 18 quintillion on a 64-bit system. This discontinuity turns a simple logic error, like checking if a loop index went 1 too far backward, into a massive positive index. It's a complete bug factory for backward loops and crucial boundary checks. This is precisely why authorities like the C++ core guidelines and Google Style Guide are so explicit. They say, and I'm paraphrasing here, do not use an unsigned type just to say a variable is non-negative. Use an assertion for that. Use signed types for the math. I'm sorry, but I just don't buy that it's simply a fossilized mistake. That dismisses the entire architectural purpose of ssize. I mean, yes, we are in a 64-bit world now, but we have to acknowledge why that decision was made, because the semantic purpose is still there.
Go on.
Think back to the 1980s, to a 16-bit environment. A signed 16-bit integer could only address up to 32 kilobytes of memory. So if you needed an index or a size for a block larger than that, you were just stuck. Using ssize, which is unsigned, allowed the system to use all 16 bits to index up to 64 KB. If the standard had mandated signed types for sizes back then, it would have essentially halved the physically addressable memory range. It was an essential tool for modeling the entire available memory space.
A necessary evil of the time, perhaps.
More than that, more fundamentally, using size t is semantically precise. A container size or an array index is a measurement of a physical quantity. It cannot logically be negative, can it? When we use size t, the type system enforces that non-negative constraint. It provides a layer of safety by making negative values just conceptually impossible. And furthermore, Systems programming relies on behavior that is mathematically precise. Unsigned arithmetic models the ring of integers modulo 2 to the n. This just means that wraparound, where uintmax plus 1 is guaranteed to be 0, is strictly defined. That predictable behavior is crucial for low-level tasks, like, say, cryptographic hashing or network sequence numbers, where you absolutely must rely on modulo arithmetic.
The historical necessity for 32K-Bs is acknowledged, sure, but that argument is now completely inert. Today, a signed 64-bit integer can address 9.22 exabytes. We are not running out of address space. The concern has fundamentally shifted from address capacity to address safety. And that subtraction trap you mentioned isn't some abstract logic error. It's a distinct and prevalent security vulnerability, CWE 191. This exists because when a subtraction causes an unsigned variable to underflow to that massive positive value, that value is then often immediately used in, say, a memory allocation or a copy function.
Okay.
The real-world example here is the 2015 Android Stagefright vulnerability. Attackers manipulated a media file containing unsigned chunk sizes. When the system was calculating buffer space, these sizes caused an integer underflow, wrapping the size around. The outcome was disastrously inconsistent. The system used the wrapped small size to allocate the buffer, but then used the original massive pre-wrapped size in a memcopy. That small buffer was immediately overwritten by billions of bytes, leading to a catastrophic heap smash and remote code execution. The underflow was the precise exploit vector.
I agree that stagefright is a textbook case of an integer vulnerability, but I challenge the idea that the problem is the existence of unsigned types. I'd argue the danger in C++ is the language's implementation of implicit conversion hazards. The standard library basically forces the developer to mix signed and unsigned types because size it is everywhere.
Right, the mixing is a problem.
Let's walk through the disaster scenario, because this is the core failure. Say you have a signed integer s equal to -5 and an unsigned integer u equal to 10. When you compare them, you check if s is less than u. The C++ standard mandates the usual arithmetic conversions. Because unsigned integers have a higher conversion rank here, the signed integer s gets implicitly converted to unsigned. The value -5 as a 32-bit unsigned int becomes 4,294,000,000 and so on.
A huge number.
Exactly. So now the comparison SU becomes a comparison between 4 billion and 10. Since 4 billion is clearly not less than 10, the expression incorrectly evaluates to false. This logically incorrect comparison allows dangerous loop conditions to proceed or boundary checks to fail silently. It's this treacherous forced mixing, a direct consequence of the standard library demanding size t, that leads to these bugs, not the inherent value of unsignedness.
That is a compelling point about the conversion rules. And you're right, C++ hazards amplify the danger. However, the entire premise of needing those conversions just evaporates if we adhere to a signed-by-default philosophy. If the index and the size are both signed, the conversion risk just disappears.
But the system architecture demands defined behavior. We rely on the fact that unsigned overflow or wraparound is strictly defined. We need that predictable modulo behavior for things like low-level protocols, TCP, crypto algorithms. I need to know exactly what happens when I increment past the max value. I need it to wrap to 0. Signed overflow, by contrast, is just undefined behavior, UB.
Okay, but
And consider bitwise operations. Unsigned types are the only sensible domain for manipulating raw bits, masks, flags. When you right-shift an unsigned integer, it's always a logical shift. Zeros get inserted on the left. That's essential. If you use a signed integer, you risk an arithmetic shift, where the sign bit gets extended, which can corrupt your data or hit implementation-defined behavior.
I see why you'd emphasize defined behavior for those specialized components, but let me give you a different perspective, one that comes straight from, the compiler optimization pipeline, which is equally critical for modern high-performance systems. The undefined behavior of signed overflow. It's not a weakness, it's a feature that gives the compiler immense leverage.
A feature?
Yes, because the compiler is permitted to assume that signed overflow never happens, otherwise the program's state is just undefined. It can make powerful simplifying assumptions. This enables techniques like scalar evolution, or SCEV. When the compiler sees a loop with a signed counter, for int I equals 0, it can confidently prove that I plus 1 will always be greater than I. It assumes the loop will terminate because if it didn't, it would have overflowed, which is UB.
Okay.
If you use an unsigned counter, however, the compiler is forced to be conservative. The standard requires it to preserve the possibility that I plus 1 could wrap back to 0, meaning I plus 1, I is a real possibility. This uncertainty cripples that CEV analysis and often prevents the compiler from calculating a reliable trip count for the loop. The consequence? Slower code. Compiler passes like Vectorization, or SIMD, rely on the compiler being able to prove the loop terminates predictably. If it can't safely vectorize it. Using unsigned types can force the compiler to insert expensive masking instructions or runtime checks, resulting in measurably slower code. So, signed integers are often superior not just for safety, but for performance in general application loops.
That's a fascinating counterpoint, but it relies on accepting a non-deterministic crash at the boundary as an acceptable cost for optimization. I mean, if real-world data hits that 2 to the 63 barrier, your theoretically fast code causes an unpredictable failure. We're trading reliability for marginal speed gains. And look, if we accept safety as paramount, we have to return to managing the real-world standard library. Its inertia is the single biggest barrier to adopting your signed-by-default philosophy.
And yet, the consensus among systems architects has demonstrably shifted, which is why the Standards Committee acted. Look at std.ssize in C++20. This function takes any standard container and explicitly returns its size as a signed integer, ptr to fifth. This was introduced precisely to allow developers to get a container size and immediately enter safe, signed arithmetic without any conversion issues. This is the C++ standard providing an escape hatch, sanctioning the signed camp approach without an ABI-breaking redesign of std vector. It's a monumental sign of consensus change.
I agree that ssize is a necessary mitigation, but I would frame it as a bandage covering a deep wound, not a sign of fundamental change. The inertia of the existing standard library and the commitment to consistency is just too strong. I mean, consider the debate around std.span. Bjarne Stroustrup, the creator of C++, argued vigorously that span.ssize should be signed. He called the choice to keep it unsigned a bad mistake. Despite that powerful push, the committee voted to keep it unsigned as ssize, prioritizing consistency with std.vector over theoretical safety.
A political decision, then.
A practical one. It shows how fundamentally the ecosystem remains tied to the unsigned model for memory boundaries. We can't just mandate that people use signed types when the core language infrastructure continually forces unsigned usage on us. I mean, look at a language like Rust. They use unsigned indexing, ssize, but they achieve safety by doing two things C++ refuses to do. They ban implicit conversions between signed and unsigned types entirely, and they enforce strict debug checks that cause a panic on overflow. This proves unsigned types aren't inherently dangerous. C++'s rules are what make them dangerous.
And that's where we agree in principle. The danger is amplified by C++'s rules. But the path of least resistance to safety today is managing the types we can control. While ssize is fixed for ABI stability, general application code should adhere to a signed-by-default philosophy. Use int for loop counters, use std.ssize on container sizes, and enable sanitizers to catch any unsigned wraparound that slips through. In modern 64-bit systems, the risk of massive, exploitable memory safety violations far outweighs any perceived benefit of semantic purity or that defunct extra bit of address space.
I'm just not convinced by that, because it advises abandoning a tool that is functionally required for low-level systems programming. Unsigned types are an inescapable reality for dealing with physical memory, bitwise protocols, and the existing STL. The true engineering task isn't avoiding them, it's mastering them. We have to isolate their usage to where they are functionally required, bit masks, specific modulo arithmetic, and meticulously manage C++'s treacherous implicit conversion rules. Simply advising don't use unsigned pushes the complexity onto the developer to manage mixed type expressions, which is precisely where the bugs lie.
Well, this debate ultimately represents the clash between two, I think, very valid systems engineering perspectives. The necessity of precisely modeling hardware reality with defined modulo arithmetic versus the necessity of modeling mathematical intuition for robust application logic and security.
And the material certainly provides ample evidence for engineers to decide which trade-off safety from underflow errors versus semantic clarity for memory representation serves their specific architectural needs best.